Today we are going to explore one of the most fascinating and forgotten stories of medieval metallurgy, bog iron, a natural resource that entire communities harvested as if it were an agricultural crop. Before continuing with the video, remember to subscribe to the channel for more documentary narratives like this. Imagine for a moment a waterlogged landscape in northern Europe, where the morning mist hangs over dark waters and peat has accumulated over centuries. Your feet sink into the reddish mud, and the air carries the distinctive odor of decaying organic matter. To untrained eyes, this scene is nothing more than an obstacle to be avoided. But more than 1,000 years ago, a medieval blacksmith would have immediately recognized what lay hidden in that foul-smelling mud. He would have knelt down and begun to dig, because within that soil there was iron. Not ore buried by geological forces or extracted from deep tunnels, but iron that had grown there, deposited grain by grain over decades by bacteria and groundwater, waiting to be harvested like a crop. This is the story of how medieval communities transformed swamp mud into metal, and how that metal possessed a property that modern steel still struggles to achieve. To understand bog iron, it is first necessary to understand what happens at the chemical level inside a peat bog. Iron dissolves into groundwater from the surrounding rocks and soils. In the oxygen-poor environment underground, it remains in a soluble form called ferrous iron, essentially invisible, dissolved in the water like salt in seawater. But when this iron-rich water rises to the surface through springs or seeps into wetlands, something fundamental changes. It encounters oxygen. The ferrous iron oxidizes into ferric iron, which is insoluble. It precipitates out of the water as solid particles of iron oxyhydroxide, mainly a mineral called goethite. These particles accumulate in the peat, in sediments around plant roots, forming layers of porous and brittle material with a rusty orange color. This process is not only chemistry, it is also biology. Specific bacteria, particularly species such as Thiobacillus ferrooxidans, act as catalysts in this transformation. They oxidize the iron enzymatically, concentrating it as part of their life cycle. And there is a visible sign that reveals the presence of these bacteria without the need for any equipment. They leave a distinctive film on the surface of still water, a sheen that looks like oil, but is actually a gelatinous precipitate of iron hydroxide. If someone touches it, it shatters like thin glass rather than flowing like oil. Medieval iron gatherers knew this sign well. That iridescent film was an unmistakable marker. There is iron here. The truly remarkable feature of bog iron lies in its ability to regenerate. Economically useful deposits can reform in approximately 20 years after harvesting. The same bog could be worked once per generation. The surface peat was removed, the iron nodules were extracted, the peat was replaced, and then people waited. 2 decades later, the bacteria and the groundwater would have deposited a new metal harvest. This makes bog iron one of the only renewable metal ores in human history, a resource that regenerated naturally while communities were using it. Medieval communities across northern Europe organized entire economies around this resource. In Scandinavia and Finland, bog iron dominated iron production roughly between the years 500 and 1300 CE, a period of 8 centuries of continuous use. In Iceland, large-scale production sites, known as iron farms, operated specifically to harvest and smelt bog ore. Smaller rural properties also practiced it, producing only enough iron for self-sufficiency. In Hungary, more than 300 early medieval smelting workshops have been excavated by archaeologists, many of them processing local peat bog ore. The process of turning bog mud into usable iron followed a sequence that was fundamentally the same in all these regions. Although there was no direct contact between many of them, the universality of the method suggests that it was not invented once and then spread everywhere. It was discovered independently many times because the logic of the process is almost self-evident once the material is understood. The first step was gathering. Medieval ironworkers identified bog ore deposits by reading the landscape. They looked for withered grass, waterlogged ground with moisture-loving vegetation, and reddish-brown discoloration in nearby water. Once a deposit was located, they used wooden or metal probes, pushing rods into the soft ground to detect heavier concentrations of ore beneath the surface. They then cut through layers of peat with special knives and extracted the ore by hand. Some deposits contained pea-sized nodules scattered through the peat. Others formed larger crusts and plates. The second step was roasting. The collected ore was wet, often saturated with bog water. Before it could enter a furnace, it had to be dried and partially purified. Workers spread the raw ore over a bed of wood and set it on fire. The heat, reaching approximately 600 to 800 degrees Celsius, drove off moisture and burned away volatile impurities, especially sulfur. Too much sulfur makes iron impossible to work, causing it to become brittle and crack during forging. Roasting also made the ore more porous and easier to crush into smaller fragments, which improved gas flow during smelting. The third step was the smelting itself. Medieval smelters built bloomery furnaces from local clay, typically conical structures 70 to 100 centimeters high, with an inner diameter of 30 to 40 centimeters. The furnace was charged with alternating layers of charcoal and crushed roasted ore, in roughly a 1-to-1 ratio by weight, adding 7 to 15 kilograms of ore incrementally over the course of 2 to 4 hours. Air was supplied through a clay tube called a tuyere, connected to hand-operated bellows. Smelting temperatures reached between 1,100 and 1,300 degrees Celsius. This point is crucial for understanding the process. The melting point of pure iron is 1,538 degrees Celsius. Medieval furnaces never reached that temperature. The iron never became liquid. Instead, at the lower temperatures of the bloomery furnace, the iron oxide in the ore was chemically reduced by carbon monoxide from the burning charcoal. Oxygen was stripped away, leaving behind solid particles of metallic iron that welded themselves together into a spongy, porous mass called a bloom. Meanwhile, the unwanted materials, silica, alumina, and various other impurities smelted into liquid slag that flowed downward and out of the furnace. The yield was modest. A bloomery furnace typically converted only 10 to 20% of the iron contained in the ore into usable bloom. The rest was lost in the slag. But the bloom that emerged was real iron, ready for forging. The fourth step was consolidation. The bloom came out of the furnace full of trapped slag, charcoal fragments, and voids. It had to be hammered repeatedly while hot in order to drive out impurities and compress the metal into a solid, workable bar. This was exhausting physical labor. Each blow squeezed out pockets of liquid slag and welded the iron grains more tightly together. The result was wrought iron, a low-carbon iron that could be shaped into tools, nails, hinges, knives, and weapons. This is where the story becomes genuinely interesting from the perspective of material science. Modern industry treats phosphorus in steel as a contaminant at concentrations above roughly 0.04%. Phosphorus causes what metallurgists call cold shortness, a form of embrittlement that makes steel crack under impact, especially at low temperatures. Every modern steel specification sets strict upper limits on phosphorus content. but bog iron ore is naturally rich in phosphorus. Chemical analyses of bog ores from Somogy County in Hungary found concentrations of phosphorus pentoxide between 3 and nearly 5% by weight in the raw ore. This phosphorus transfers into the iron bloom during smelting. The resulting metal, which researchers call phosphoric iron, typically contains between 0.5 and 1.5% phosphorus by weight. By modern standards, this is an absurdly high phosphorus content. No modern steel mill would intentionally produce it. And yet, archaeometric studies across Europe have confirmed that phosphoric iron was not a defect. It was deliberately used throughout the medieval period. Why? Because phosphorus does two things that medieval smiths discovered empirically, centuries before anyone understood the chemistry. First, phosphorus increases hardness. A blade of phosphoric iron holds an edge better than pure wrought iron. Medieval knife makers exploited this by using phosphoric iron specifically for cutting edges. Second, and more important to our story, phosphorus increases corrosion resistance. Iron made from bog ore, with its residual phosphorus and often with silicate inclusions that form a glassy surface coating, resists atmospheric rusting significantly better than ordinary wrought iron or modern mild steel. This was not theoretical knowledge to medieval craftsmen. They could see it with their own eyes. The most dramatic demonstration appeared in pattern-welded sword blades. Between the 5th and 14th centuries, European swordsmiths created blades by forging and welding together alternating strips of different kinds of iron, then twisting them and grinding them to produce serpent-like patterns on the blade's surface. Bog-derived phosphoric iron was used as one of the contrasting metals, precisely because it corroded at a different rate from the layers of ordinary iron and steel. When the blade was etched with mild acid, the phosphoric iron remained bright while the other metals darkened, creating striking visual contrast. Researchers at the Budapest University of Technology confirmed this through smelting experiments. The Vikings took bog iron to places where no Europeans had ever smelted iron before. Around the year 1021 CE, Norse explorers established a settlement at what is now L'Anse aux Meadows, at the northern tip of Newfoundland in Canada. Archaeologists recovered 98 nail fragments and numerous rivets from the site, along with 15 kilograms of slag. Analysis of the slag confirmed that it matched bog iron. The Norse had located a local bog, harvested ore from it, smelted it on site, and forged nails for ship repair. This was the first iron production in North America, and it was carried out using bog iron. A single Norse longship required approximately 7,000 nails, forged from about 400 kilograms of finished iron. Producing that amount of iron from bog ore meant that a smith would need to process approximately 30 tons of raw ore. Bog iron smelting was common knowledge, not a trade secret restricted to master craftsmen. In Russia, bog ore remained the main source of iron until the 16th century. In colonial North America, bog iron was extensively harvested along the East Coast. During the American Revolution, cannonballs were cast from bog iron for the colonial forces. Across central and southern New Jersey, bog iron was smelted and forged into tools and structural wrought iron railings, specifically valued for their natural resistance to rust. Many of these railings still remain on buildings in Trenton and Camden, still intact, still supporting staircases and balconies. Meanwhile, modern mild steel exposed to the same coastal air begins corroding within months. So what happened? Why did we stop? The answer is not that we found something better in every respect. The answer is that we found something cheaper and faster. The transition began with the development of coke-fired blast furnaces in the 18th century. These furnaces could process mined ore, particularly hematite and magnetite, at temperatures and in volumes vastly greater than anything before. Production scaled from kilograms per day to tons per day. The economics were overwhelming. But there was a trade-off. Blast furnace iron and the steels derived from it have compositions fundamentally different from bog iron. The phosphorus that gave bog iron its corrosion resistance was now considered a contaminant to be removed. The silicate inclusions were also eliminated. The new steel was stronger, more uniform, more available, and vastly cheaper. It was also far more vulnerable to rust. And so we entered the modern age of metal corrosion. According to the Federal Highway Administration and NACE International, rust costs the United States $276 billion every year. The global cost of corrosion is estimated at $2.5 trillion annually. We did not solve the problem of rust. We scaled it up. There is an irony in the modern approach to corrosion that a medieval blacksmith would have found baffling. We produce steel that rusts easily, then spend enormous sums applying coatings and treatments to keep it from rusting. Modern weathering steel, sold under trade names such as Corten, tries to imitate part of what bog iron does naturally. It is a good material, but it is worth noting that medieval bog iron achieved a similar effect using nothing more than the natural chemistry of a marsh. The experimental archaeology community has kept this knowledge alive. These experiments confirm something important. The process works. It is labor-intensive and slow, but the iron it produces is real, functional, and in some measurable ways superior to modern alternatives in applications where corrosion resistance matters more than volume. For anyone interested in self-sufficiency, the conclusion is this. Smelting iron from bog ore is one of the very few metalworking technologies that can be carried out entirely with hand tools and natural materials. No mines, no industrial furnaces, no electrical grid. Only knowledge, labor, and a bog. More than 1,000 years ago, a Norse explorer landed on a rocky shore in Newfoundland. The nails he forged were recovered by archaeologists a millennium later. They had survived 1,000 years in acidic, waterlogged soil. Today, a standard galvanized nail loses its protective zinc coating in 15 to 20 years in a marine environment. The Viking nail is in a museum. The modern nail is in a landfill. We have not advanced beyond medieval metallurgy in every respect. In some very specific and measurable ways, we chose speed and scale over durability. The story of bog iron is ultimately a story about what we value. Medieval blacksmiths valued durability because they had no choice. We value speed and scale because we can. The next time you see a reddish stain in a stream or an iridescent film on the surface of still water, remember that you are looking at the same sign that guided medieval smiths to their ore deposits. The iron is still there, growing slowly, waiting for anyone with the knowledge and patience to harvest it. If you learned something new from this video, consider subscribing to the channel. Thank you for watching, and I will see you in the next one.